Hi everyone, my name is Sabina Gera and I will briefly tell you something about the topic chemical, toxic and radioactive properties of depleted uranium, which is processed within the Model 2. This model aims to provide a basic understanding of the properties of depleted uranium, as well as to emphasize the importance of knowing the chemical, toxic and radioactive properties of depleted uranium in relation to humans and the environment. After listening to this part of the Model 2, I hope you will be able to describe uranium and depleted uranium, to outline the chemical, toxic and radioactive properties of depleted uranium, and also to relate the chemical, toxic and radioactive properties of depleted uranium to humans and the environment. In order to understand the chemical properties of depleted uranium, we need to define the basic terms and concepts and definitions related to uranium, nuclear fission, depleted uranium, effect of depleted uranium on humans. When was uranium discovered? Is discovered in 1789 by Martin Heinrich Klaproth, named after the planet Uranus. Pure uranium is a radioactive silvery metal that quickly oxidizes in the air. The table on the slide shows the basic data for uranium. Naturally occurring uranium consists of a mixture of three isotopes: 99.27% of uranium-238, 0.72% of uranium-235, and 0.0055% of uranium-234. The discovery of uranium's radioactivity was made in 1896 by Heinrich Becquerel in Paris, who left a sample of uranium on the top of an unexposed photographic plate. This marked the discovery of the radioactivity. To Becquerel's surprise, the plate fogged up, indicating the emission of some sort of radiation from the uranium salts. Becquerel shared the Nobel Prize with Marie and Pierre Curie in 1903 for this discovery. The picture shows Becquerel at the table with the large magnet in the laboratory. The half-life of uranium-238 is 4.5 billion years. It undergoes the decay process, ultimately leading to the formation of radium-226, which in turn undergoes a further decay process to form radon-222. Radon-222 subsequently undergoes a decay process, leading to the formation of polonium-210. This, in turn, undergoes a further decay process, resulting in the formation of stable nuclide lead. The table provides basic data on the oxidation states and isotopes of uranium. Uranium can exist in the +3, +4, +6, and +5 and +6 oxidation states. The +4 and +6 states are the most common in the environment. Uranium is a naturally occurring heavy metal that can be found in almost all parts of the environment, in water, soil, and the rocks. Ingesting or inhaling large concentration of uranium can cause severe health effects. Uranium that has been enriched into a uranium-235 concentration can be used as a fuel for nuclear power plants and the nuclear reactors that run naval ships and submarines. As previously stated, the natural uranium is composed primarily of uranium-235 and uranium-238. Neutrons colliding with uranium-235 emit huge amounts of energy through a fission reaction. Uranium-238 is less fissile than uranium-235. Natural uranium consists only approximately of 0.7% of uranium-235. So isotope separation, uranium enrichment is needed to increase its content to 3 to 5% for use as a fuel for light water reactors. It is therefore essential to understand nuclear fission. Nuclear fission is defined as a nuclear reaction where the nucleus of an atom splits into two or more smaller nuclei while simultaneously releasing energy. To illustrate, when a neutron strikes the nucleus of an atom, uranium-235, the latter splits in two smaller nuclei, namely a barium nucleus and a cryptonucleus, accompanied by two or three neutrons. The additional neutrons subsequently impact other neighboring uranium-235 atoms, which will also undergo fission and generate further neutrons in a self-amplifying process, thereby initiating a chain reaction in a matter of seconds. With each instance of the reaction, a release of energy occurs in the form of heat and radiation. The heat can be converted into electrical energy in a nuclear power plant in a manner analogous to the conversion of heat from fossil fuels such as coal, gas, and oil into electrical energy. To produce fuel for certain types of reactors, higher concentration of uranium-235 are essential for nuclear fission. This is why natural uranium is enriched in uranium-235. And the picture on the slide shows the described process. Once the uranium is enriched, it can be effectively used as a nuclear fuel in power plants for 3 to 5 years, after which it is still radioactive and had to be disposed of following lines to protect people and the environment. And the question is, what is depleted uranium? Depleted uranium is a byproduct of the process used to enrich natural uranium for use in nuclear reactors and in nuclear weapons. Depleted uranium is a mixture of the same three uranium isotopes, uranium-238, uranium-235, uranium-234, but with very little uranium-235 and uranium-234. Depleted uranium containing mostly uranium-238 is an effective radiation shielding material and an excellent projectile for armor-piercing weapons. It is also used as a counterbalance on helicopters, rotors, or airplane control surfaces as a shield to protect against ionization radiation, as a component of munitions to help them penetrate enemy armored vehicles, and as armor in some parts of military vehicles. This is uranium with percentage of uranium-235 lower than the 0.7% by mass containing in natural uranium. Blending depleted uranium with highly enriched uranium, such as that form weapons, is an effective method for producing reactor fuel. Depleted uranium is 1.7 times denser than lead, which is why it is used in industry. It has also been used for civil and military purposes for many years. Depleted uranium exists in any chemical form in which uranium occurs. Metallic uranium is among the densest material known, with a density of 19.1 gram per cubic centimeter. It is a shiny silver gold metal. It is pyrophoric when in a chips or powder form. Upon exposure to air, it readily oxidizes to form a layer of yellow-green and or black oxides on the surface. Depleted uranium potential impact on human health and the environment is a subject of concerns and debate with various influencing its. The inhalation of depleted particles that persist within the lungs for extended period may result in the damage of lung cells and an elevated risk of developing lung cancer over time. The primary hazard associated with depleted uranium is internal, although external radiation hazards do exist, as the progeny of depleted uranium emits gamma rays. The principal biological risk associated with depleted uranium is not its radioactivity, but rather its chemical toxicity. Similarly, as with mercury, cadmium, and other heavy metal ions, elevated levels of uranyl ions have the potential to impact the kidneys. High concentration in the kidney can result in damage, with the potential for renal failure in extreme cases. Efforts to depleted uranium contamination and monitor affected populations are ongoing, but the long-term environmental and health consequences remain a matter of significant concern. Thank you for your attention.